recording. Okay, so Luuk, yeah, you can start, please. Yeah.
Yeah. So as the title suggests and the abstract told you guys, I'm going to be talking about the analytic torsion of a standard cone, and we'll talk about what a standard cone is. I will say my goal was to find the analytic torsion of a standard cone and the Reidemeister torsion for at least like a simple example. I didn't finish that, so we'll just. I hope this is this might not take the full hour. Is what I'm getting at. So analytic torsion of a standard cone. The goal of today is to show that the analytic torsion of a party hat is this expression here. That's going to be like our nice example at the end. But in general, we'll find an expression for the analytic torsion of a cone over a closed manifold N. So the interesting part of this is that while N satisfies all assumptions we had in the course, it's a closed manifold, it's nice, there's very nicely behaved zeta functions. A cone over a manifold is in general not a manifold, it's a pseudo manifold. So we can see this in the definition of the stack.
Let me ask the question about the formula. So this is independent of the height of the cone, you mean?
For height 1.
Oh, okay, right. So is this okay, right? Okay.
Yeah.
Very good. Yeah.
So if you can, of course, scale the entire thing and then work with small r.
Okay, so there's a similarity factor which is irrelevant. I see. Okay.
Yeah.
Okay.
It simplifies a lot of the formulas nicely if r is 1, and we'll see that simpler formulas is a thing we want in this context.
Excellent. Very good. Yeah.
So the standard cone over a manifold is the product. So we have a height for our cone, which we'll always be calling the x coordinate, and we have our the base of our cone. So for the party hat, we'll eventually be talking about n is just a circle. And then if you have a circle, so you get a circle and a nice cone over it. So this part is sort of encoded in the 0, 1 with this metric. And the problem that, well, the thing that takes the most work to get rid of is the singularity at a tip. So this cone, as I mentioned, is not a manifold, it's a pseudo manifold because it has a singularity up here. It's a conical singularity, which is sort of the easiest singularity to deal with. Next up would be edges on your space, and then you can go very far from there. But this being the simplest, and this being like one standard cone, so you can do a lot of this work for a manifold with multiple conical singularities. There is a lot of things are known about behavior of the zeta functions. But I like this example because it's really a nice specific example. Okay, so what's the plan? First of all, we're going to prove something we call a separation of variables. So we want to separate the spectral parts coming from n and the spectral parts coming from the conical part. So that will be our first step. Then we split the entire Ram complex into subcomplexes, and this I think is a pretty cool idea. It uses Hodge decomposition and a couple of other things we talked about in this course and in the index theory course. So it's kind of cool. It also gets a little bit messy at times, so I haven't included the full computations in this talk. But basically the idea of chopping this guy into subcomplexes is that, you compute the contribution of each subcomplex to the zeta function, and then you sum over all these subcomplexes. Then the third, as I said, the third step is for each subcomplex, find its contribution to logarithm of the analytic torsion. And then step 4 is just sum everything together. So that's also the sort of outline of what we're going to be talking about for the next bit of time. Okay. Oh, right. And so this is all based on pretty much one paper written by Wertmann. I think he's German, from 2009. Okay. So what is this separation of variables? Basically, we're going to write K-forms on M, which we have over here. So compactly supported away from the boundary and the singularity. The K-forms consists of sort of a part that's a K-form on the base manifold and a K-1 form on the base manifold, wedge dx. So that's what we see happening here. So we have our K form on N and our K-1 form on N wedge dx, which is the sort of the general form for a K form on M. And then these factors here, these factors here make this an isomorphism of L2 spaces. So if we, sorry?
So the brackets in the formula for psi k, is this C infinity of C interval 0, 1 into omega k minus 1 n only, right?
No, into both.
Oh, even to omega k, you have to have this interval mapped into that as well, I see.
Yes.
Uh-huh.
Because you have you essentially have a copy of N at every height, right?
That's right. Yeah. There is yeah. Okay, right. No, that's fine.
Yeah. So yeah, you can prove that this is a bijection, and then if you check the L2 norms on both sides, these factors here make it a isomorphism of L2 spaces. Even.
Does it also commute with differentials, this map phi? I mean, psi?
No, so I think that's the next thing. So we compute D in this split form, because the split form is what we're going to be working with. So we want to know what D looks like. And you can compute like this is a very straightforward computation, really. Yeah, so then using this, I forget exactly what's on the next slide. Yeah, so because these psi k's, these separation of variable maps, are isomorphisms of L2 spaces, if we define our delta k, so this is the Laplace operator in the separated picture, just as sort of the basis transformation of our regular Laplace operator, then they have the same spectrum, because they are, you can just use psi k to move your eigenfunctions back and forth. So a major theme in this paper are boundary conditions. And if you go into the analytical details of working with self-adjoint operators in L2 spaces, choosing boundary conditions corresponds to choosing a domain for your operators. So in this case, we choose what's called the relative self-adjoint extension of the Laplacian, which is defined by this formula. So we take the minimal extension of the differential, and then we use the adjoint of that. And that is going to be the maximal extension of the formal adjoint. So this is a bit of, I don't know how familiar everyone is with unbounded operators and their domains. But basically, the formal adjoint is just what you'd normally call the adjoint, but its domain changes. So the smaller the domain of your starting operator, the bigger the domain of your actual adjoint. So which is why d star of the minimal extension is going to be the maximal extension of the formal adjoint. And you get self-adjoint operators if you pick a domain that's sort of halfway in between, which is why this works, because we're combining the minimal and the maximal domains of the differentials. That's sort of the heuristic explanation of why this guy is self-adjoint and why this is a self-adjoint extension. The actual proof is just a lot of throwing around definitions. It's not particularly insightful. As soon as you realize that you want to be sort of halfway between the minimal and maximal extensions. You can actually evaluate what concretely these boundary conditions are. So we want our separated functions, our separated forms, to satisfy these two boundary conditions at the sort of the big end of our cone. So at the, if we just consider our standard cone, so the boundary conditions over here, because the base manifold is a boundary for your bigger manifold. So you want the boundary conditions there to be these two we have down here. So on the K part, we have Dirichlet conditions. And on the K-1, these are Neumann conditions, but they're translated. So it's kind of a weird mix between Dirichlet and Neumann conditions. And to be honest, I don't fully understand why we choose these, except that over here, this is a very nice way of defining a self-adjoint extension. These boundary conditions are kind of out of the blue, at least for me. So just another small side note. If you're working on L2 spaces, this expression is already kind of confusing, because if phi is an L2 function, its value at a specific point is not defined. So there is another piece of machinery that goes into actually making sense of what it means to be a boundary condition. So that's sort of an interesting aside. Right. So using the special form of dk that we had here, we can just compute the kth order, like degree k Laplacians. It's just this guy times its conjugate. And it turns out that it's of this form. So minus ddx squared plus 1 over x squared times some second order elliptic differential operator on this sum of spaces. So the paper also mentions your first idea might be to, well, AK is an elliptic differential operator. It has eigenfunctions, etc., etc. So we might try to decompose or find the eigenvalues of the kth order Laplacian using this operator AK. But this turns out to be problematic because we are working on a non-closed manifold. We have boundary conditions to consider. And it turns out that the boundary conditions of AK might be, and I think are, I haven't actually checked, but they might be incompatible with the boundary conditions for Laplacian K. So I have a little bit of an example. I'm not really happy with this example, but it does kind of show what kind of things can happen. So if you consider this operator, so it's your standard ddx squared, but shifted. And let's say Dirichlet boundary conditions. So we can write the space of functions on which it acts as a sum of eigenfunctions for L0. But these are not eigenfunctions for L alpha. right? So this decomposition isn't compatible with L alpha. So if you have like a sum of operators, you can't just pick eigenfunctions for one and use them for the other. Sorry, I know this is a bit vague, but we can come back to this if we want at the end. So when do we say a decomposition is good or compatible? Well, first of all, your operator needs to preserve the decomposition. So you want the image of H1 to be inside H1. And sort of the important thing, the thing that tends to break, is that if you have a sum of two things that are in the domain, then both summons separately have to be in the domain. So in terms of Dirichlet boundary conditions, you might have something like phi1 of 1 is -1, phi2 of 1 is 1, so that their sum, so the sum of these two satisfies Dirichlet boundary conditions at 1. But separately, they do not, which means that this is not a good decomposition, because you want separated parts also to satisfy your boundary conditions. That's that's the main point of these compatible versus incompatible decompositions. And then for the structure you're working with, it turns out that you can check if a decomposition is compatible just by using these sort of constituent operators. As long as they sort of preserve the decomposition nicely, it's a good decomposition. And again, the proof of this is just juggling domains. It's not super exciting. At least as far as I've seen, there's nothing too interesting going on there. So we get two types of subcomplexes, type 1 and type 2. Type 1 is the problem case, so we'll start with that. So what do? Is we start from co-closed K-forms, so d star of psi is 0, and psi is a K-form, that are eigenfunctions for the Laplacian on n on the base manifold, for non-zero ones. So the subcomplex of type 2 is going to deal with harmonic forms. Type 1 deals with the non-harmonic forms. Okay, so then defining these four vectors, we can get a subcomplex like here. So this is in order k. Yeah, this is order k. So let me just write it like this. This is in omega k of m. This is part of omega k plus 1 of m. And this is of inside. Right, because psi 1 is 0 psi, so we have a k form in the second component. So that's a k form on m. For this middle one, we have two contributions because we want this to be a subcomplex. We have both psi comma 0, so that's a k form in the first slot, which means it's a k plus 1 form on m because we wedged this dx on it. And we have the d of psi. And then finally, we have the d of psi in the first slot. And this 1 over root eta, eta is its eigenvalue. This is just a nice normalization that makes things a bit nicer. And it turns out that this is a subcomplex. Oh, well, you can see that this is a subcomplex, right? So we take functions from 0, 1 with values in this. So if you remember, the d is -1 to the k dx plus 1 over x dn, some constant dn. So you can check that if you plug in some function with values like a scalar times 0 psi, and you run it through this guy, you end up with a linear combination of these two. So let's just say it something like this. So f times 0 psi maps to f prime times psi plus, well, let me not do this here. Sorry, I probably should have included this on the slide or something. So because we have both psi over here and the d of psi over here, that sort of corresponds to this line here, right? We need both its differential and constant multiples of it. So you get that this guy is a subcomplex of, well, in the separated picture, it's a subcomplex. So for this subcomplex, we can compute the Laplacians, and they turn out to look like this. And this is sort of the model operator that we're going to keep coming back to. This is the central thing, pretty much. And you can sort of see that these etas are the eigenvalues for delta n, right? So these come from, these are eigenvalues on the base manifold. And you can see that it's not just these that show up in this decomposition, it's this plus this entire thing. And this has to do with the compatibility of the decomposition. You can check the domains. And so because this is a compatible decomposition, the domain of these two operators are just the domain of the operator, like the complete operator, restricted to this subcomplex. Now you might notice this is a complex with 3 entries, and I've only shown 2 Laplacians, which is why I'm saying like these are the outer Laplacians. There's also a Laplacian on this middle vector space, of course. You can compute it. I did. It's almost, so it's a 2x2 matrix because the middle thing is two-dimensional. And it looks something like, so delta 0 on the diagonals, which are just these guys. And then there is some terms over here. I don't remember off the top of my head what these terms are, but so it's not a very nice thing. And the cool part is it later turns out that in the analytic torsion, the contribution of this guy cancels out. So the contributions of this term and this term cancel out the contribution of the middle Laplacian, which is a very specific thing that happens for this type of complex. But it's cool, and we'll see this in more detail later. So the second type of subcomplex are the harmonic forms. So it's a little easier. Pretty much all of the discussion of the previous type carries over here. It's a compatible decomposition. You can check the domains of the Laplacians are nice. And they both turn out to, again, be of this form. And again, we'll see that the Laplacian over here and the Laplacian over here will cancel partially in this case. Right. So this is a very full slide. And I just want to show you how, like, what does this decomposition look like in full? Right. So this here, each line, this, for example, would be omega 0 of n. So we first write omega 0 of n as omega minus 1 of n, which is 0, plus omega 0 of n, which is not 0. And then we use Hodge decomposition on both of these factors. So Hodge decomposition I've written above here. So we have the harmonic part. We have the image of D star, which you can identify with the span of co-closed eigenfunctions for the Laplacian. So in terms of the Hodge decomposition, we are more familiar with. This is the image of D star. And then this is the image of D. So this uses some completeness for the Laplacian, that you can write everything as sums of eigenfunctions. And then we do this for 2 components at a time, which is why this whole thing gets so messy. So then subcomplexes of the second type, which are dealing with harmonic functions, are over here. So each of these lines is a subcomplex of type 2. Now, subcomplexes of type 1 run like this. So together, they really decompose this entire complex. Right, so this is just sort of, I needed this to visualize how this whole decomposition worked. Because as you can imagine, the formulas get very messy. So this is a nice sort of visual help. And it gives a nice application of the Hodge decomposition. Okay, so now that we have our decomposition, let's take some time to think about what the analytic torsion is that we want to compute. So as we define it in the course, this is the analytic torsion. We showed in the course that zeta of k is regular at 0. And the method we used for that was the asymptotics for the heat trace and the Mellin transform. And it all relied on the heat trace having this asymptotics, or having these asymptotics, which we used to show that zeta function has these poles, and then the pole at 0 gets cancelled by this 1 over the gamma function. There is a problem when dealing with conical singularities, because your heat trace gets a nasty term in the asymptotic expansion. So first of all, you get root terms in the nice part, and these are okay. These won't give you any trouble for defining it at 0. However, this logarithmic term does. So these root terms are kind of associated with boundaries. They're not that bad, but this logarithmic term is really coming from the conical singularities. And if you do the same Mellin transform process, you'll find that, so there should be brackets here, by the way. So you get this, oh no, wait, never mind. You get gamma s, which has a pole of, which has a simple singularity. So 1 over gamma s has a simple pole of a simple 0 at s is 0, but we have an s squared here, which comes from the logarithmic term. So this is a problem because we can no longer define our logarithmic scalar torsion with this expression. However, it turns out very nicely that these components B, these logarithmic coefficients in different orders, actually vanish if you sum them like this. And this is a very nice coincidence, essentially, because it allows us to just move the derivative outside of the sum. So instead of the definition we had in class, we define it like this, and everything is nice and regular. So yeah, we can talk about the analytic torsion of a manifold with conical singularities. So let's look at the contributions of the different types. So the subcomplex of type 1, like its contribution is fairly easy to do, right? So we basically want to work out this sum, and because the zeta functions are just sums over eigenvalues, if we partition the eigenvalues, we can write the zeta function at order k as a sum of like partitioned zeta functions. And that's essentially the idea. We want to partition the eigenvalues into eigenvalues coming from different subcomplexes, and then compute the zeta functions of these subcomplexes. So this here is the term that comes from this subcomplex, and this is where this cancellation of the middle Laplacian happens. So we get k times the like 0 component, k plus 1 times the 1 component, and k plus 2 times this component. So then you show the idea of this part is that the spectrum of the middle Laplacian is just the union of the spectra of the outer Laplacians with multiplicity, etc., taken into account. This is special to this specific type of subcomplex, just because of how all these operators work together. You can actually show that if you have an eigenfunction here, then deep psi is an eigenfunction here. Similarly, if you have an eigenfunction here, d star phi is an eigenfunction here, and they have the same eigenvalues. Then you need some sort of completeness argument that there isn't more, right? So it could be that there is something more here, and then you appeal to the specific form of this complex and show that that doesn't happen. That means that the zeta function of delta 1 is just the sum of the zeta functions of delta 0 and delta 2. And you get this nice simplification. Okay. So this was the contribution of the subcomplex. And then there's another order of symmetry in this whole affair, and that's given by the Hodge star. So if we have this sort of this psi, this generator of our subcomplex of type 1, we can take its Hodge star and we get, well, an n minus k form a priori. But it turns out that if you sort of define a reversed subcomplex of type 1, so if you remember, like psi 1, this was psi 1, this was psi 2, this was psi 3, and this was psi 4, I think, for the normal subcomplex. If you reverse it, you also get a subcomplex of type 1. And this symmetry allows you to further cancel contributions of order k to contributions of order n minus k. And that works almost perfectly, except that the boundary conditions come back to annoy us a little bit. So for the delta zeros, their spectra are exactly the same. So their cancellation is very nice, especially if m is odd dimensional. The contribution of delta 0 just vanishes from the entire thing and cancels completely, which is really cool. But for the delta 2, the boundary conditions change. So, well, basically, these numbers here are different. So their spectra don't cancel perfectly. They cancel largely. So to find, essentially, there is 20 pages in this article figuring out what these zeta functions are. And it's a messy bit of complex analysis. So I've omitted it from this talk, partially because I can definitely follow it, but I don't feel comfortable explaining it to anyone, and because it's just a very convoluted piece of math. So let's instead look at the type 2 contributions. So this was the type 2 complex, and again, you can show using similar techniques as used for type 1 contributions that the spectra of delta 0 and delta 1 are the same. So again, you have a nice cancellation between the k and the k plus 1, and you get that the contribution of this type of subcomplex is like this. There's a further nice thing about subcomplexes of type 2, is that there's only a finite number of them. If you, let's go back a bit. So I kind of glossed over this here, but H0 to H0 isn't one subcomplex. It's like a chain of subcomplexes, one for each harmonic K form, right? But the harmonic forms of the space of harmonic forms is finite dimensional. So this is a finite number of subcomplexes, while these are all the eigenvalues of the co-closed Laplacian pop up here. There are infinitely many of these. So essentially that infinite sum of zeta functions requires that whole mess of regularization that I was talking about. So these contributions are kind of nice. And it turns out that pretty much all of the contributions rely on what they call the model operator. It's sort of the operator that keeps popping up everywhere, which is this guy, for various values of coefficient nu. And we define a range of self-adjoint extensions based on the second coefficient alpha, inducing these boundary conditions, with the special values that if alpha is 1/2, you get pure Neumann boundary conditions, but we also allow alpha to be infinite, in which case it's pure Dirichlet boundary conditions. So if this number is infinite, we just decide to ignore this one, and only consider f(1) to be 0. So the contribution of all type 2 subcomplexes together is going to be this. So there's two parts to this. So over here, we have the Betti numbers, or the dimension of the harmonic forms in order k. Right. So interestingly, it turns out it doesn't matter which harmonic form you take, they all contribute the same zeta function, or the same number to the analytic torsion, which is the regularized log of the determinant of this operator. So this is essentially the derivative of the zeta function at 0. So we have Dirichlet boundary conditions, and our value of nu is this guy, which we've seen several times. It's this k plus 1/2 minus n/2. And then, well, so our task is now to investigate this guy, because this is also the operator that pops up in the type 1 subcomplexes. Only then you have an infinite number of them, and things get even more out of hand. So it turns out that we just straight up know the regularized determinant for these operators, based on a paper by Matthias Lesch, very recent paper. Yeah, you can just compute it. It's not. So I wanted to include the computation of this, because there's a whole computation of this in the article by Verhoeven that I used merely for this, but that argument turned out to be circular. So it uses this formula to derive some other properties, and then it uses those other properties to derive this formula. So this should be infinite. But you can also just straight up show this from this particular formula. So how you prove this formula is, I'll explain it briefly, because I think it's a fun method. So we know L1/2 infinity because this is just straight up minus d dx squared with Dirichlet boundary conditions. So we know its zeta function in terms of the regular Riemann zeta function. Its spectrum is n squared pi squared. So we can work it out for this one. And then you figure out what d nu of L nu infinity is, which turns out to be, I think it's log 2 nu plus 2. But figuring this out, so I wanted to fully understand this and include this, but I'm sorry, I started too late. It took too long. It's an interesting text, though. I fully recommend anyone that's interested in this stuff to check it out. It's a cool computation. But the point is, in the end, we get the numbers we were looking for as a fairly nice, fairly simple sum. So then if you include all the work you do for subcomplex type 1, you're ready for your final result. This is the formula for an odd dimensional cone, so your base manifold is even dimensional. And there's a couple of terms I want to point out. This one, for example, so this is just, it's the characteristic, it's the Euler characteristic of your base manifold, which comes in because we had this alternating sum of Betti numbers. All right, so that's nice. We know where that comes from. Then we have this term here, which is pretty much just this sum repeated several times, right? So this log 2 is this log 2, and then this sum flips up over here. Now you may notice that we're only summing to half of the dimension, which is because we can use Poincare duality to sort of cancel bk and bn minus k, or like compare their contributions. Then this part, everything after here up to here, comes from type 1. So you can see just by the appearance of like residues and various interesting combinations of gamma functions that there's a bunch of complex analysis going on there.
Just one question, sorry. So how come the torsion of n does not appear here?
Right. Yeah, so it does, but it's hidden. So we have here in several spots.
Oh yeah, okay, right.
We have the zeta function of n showing up. So that's where the torsion of n comes in, I guess.
Right. Indirectly they appear, right?
Yeah. And for completeness sake, so this is something I think we saw at one point in class, but like zeta for some sequence comma some number is the sum. It's like a shifted zeta function. So these alpha k are, well, there's a formula in the article. And I guess these guys are sort of interesting. These are coefficients of a power series for the asymptotic behavior of modified Bessel functions. So they are universal coefficients that are known in low dimension and computable in higher dimensions. And one warning, if you end up reading Vertman's article, he instead of using the zeta function for n in terms of the spectrum of the Laplacian, he uses the square root of the spectrum of the Laplacian. I've adapted this formula to just use, so in this formula, zeta k of n is lambda in the spectrum of delta kn, 1 over lambda s. But in the article, he uses this definition. So you use the zeta function with roots of eigenvalues of the Laplacian rather than the eigenvalues of the Laplacian itself, which confused me for quite a bit of time. Okay, but this is a nasty formula. It's nice that we can compute it in generality, but let's look at the lower dimensional cases. So for a one-dimensional manifold, it's all a lot nicer. We just get this nice formula. For a two-dimensional manifold, it's a little bit more complicated, but still pretty okay. Yeah, and then once we have this formula, it's fairly straightforward to get to the analytic torsion of a party hat. So we first just do it for the circle, just radius 1, essentially. So again, we know the zeta function, it's twice the Riemann zeta function at 2s. So you can compute all the ingredients, and you find that the analytic torsion of the radius 1 party hat, which is essentially a punctured disk, is this. And then by using the scaling of the spectrum, if you scale your manifold by a constant factor, you can compute the analytic torsion for a radius r. So again, just for completeness sake, so radius r, height 1. So if you want arbitrary radius, arbitrary height, you can do something similar, just scaling both of these by the appropriate value that scales the zeta functions in a predictable way, which will allow you to get a nice expression for that. Yeah, that's it. So I know I glossed over a lot of the interesting parts, but that was because a lot of the interesting parts are very confusing and long. Yeah, if you're interested in this stuff, definitely read the article, because it's interesting stuff. It's fairly well written, but it's also very long and intensive. So thank you.
Okay, thanks, Luuk. Let's thank Luuk. Okay, so I'll just stop the video now, and then we can. Are there any questions, by the way? Okay, so let me pause the video, and then we can just discuss.